Welcome back. So this was the part which we were discussing in the last lecture, that is basically the drainage pattern and how drainage pattern can tell us about the different subsurface rocks as well as the lithology, or we have any structure, geological structures. So we will see a couple of examples in this lecture, and then we will also look at some morphometric parameters or the morphometric studies you can do using remote sensing data also, and also the topographic maps, and that again is related to your drainage basins and all that. Okay. So this is an example which I would like to share with you, which when we were working in Sondun. Sondun is an area which is located in Punjab, and basically Punjab Himachal region, and you have so you need to travel further northwest of Chandigarh, then you will reach this is the Sondun area actually. So Sondun is very much similar to what we call this Dehradun and all that. So this is an intermountain valleys, and Dun is a local word which has been used. So there is an Pinjore Dun also which exists between the sub Himalayas and the lower Shivalik hills, and this is also the same. You are having sub Himalayas and the lower Shivalik hills here. So I just want to show you a couple of things here which also based on the drainage pattern, we were able to pick up certain anomalies in terms of the landforms. So usually till date what you have learned from using the remote sensing data and all that, you can generate such maps which have been shown here. That is your what we call geomorphic map, but since we have added some tectonic features also in this, like what we see is here is the fault scarps and all that. I will just change my pointer here so that on the white you can see clearly. So this is what we have marked as in fault scarps here. So you can see this one over the fault scarps. So this portion I will just try to explain, and we will discuss this how the drainage pattern helped us in identifying such features. Okay. So in the previous one we have we were talking about the dendritic pattern, and then we were talking about the radial. So you can see the dendritic over here. This is all dendritic pattern we have. Okay. And what we were talking about the radial, that it will have some elevated portion in the center, and then it goes on the either side. Okay. So this area is basically comprised of older material, older than quaternary, and partially some portions on the top is comprised of quaternary sediments. So what we saw here was that in particularly this area okay, was like indicating very typical radial pattern. Okay. So and that was a bit surprising here, that because here we did not expect that such deformational feature will be there. And then another thing was that there was the area where we were looking at some very typical change in the channel pattern, and that was local change, local channel pattern change, that we have discussed in the previous lecture, that if you are having the local meanders, okay, development of local meanders, and then so and even if the meanders are having like tight meanders. Okay. So this basically is meandering. We are referring to sinuosity of the channel. Okay. So sinuosity of the channel is like what I will just explain that. So if you are having a channel which is flowing in the meandering pattern, and so you have some sinuosity here, but if you are having very like tight meanders like this, then we say that it is sort of an the sinusity is quite high here. Okay. So, this is how we will be able to judge if there are local development of meanders and all that, and we have looked at a couple of that does the indicators of your we can say the active tectonics, okay, or I can say that active tectonic indicators or markers also you can say. So, this we have discussed in the previous lectures. Now, let us just look at what I was talking about, the radial pattern and all that. So, if you look at this area, this is the area which is close to Nalagad and Dhana, and in previous slide, if you carefully look at, this is the area I am going to talk about right now. Okay. So, this is your Nalagad and this is Dhana area, and just to give more idea about us, that this I have already given that this is northwest of Chandigarh, and the channel which is flowing here like this one, okay, this one is your Satluj river. Okay. So, we are looking in that domain. So, what we see here is that there is a fault which is controlling this whole topography and even the drainage here. Okay. So, that what we were able to pick up, and that was quite interesting. So, let us go ahead and see what evidence we see over here in particularly this area. So, and then we will go to this part here. So, first if you look at the close up of this, what you see here is that you have a development of tight meanders locally. Okay. So, if I put the my line here which has been put here, that is your active fault around Rajpur and further down. So, this is exactly the line which passes through. Okay. So, this is the line here, and that what we have marked as an active fault. So, if I take a cross section here, say this is A, this is B, then it will appear something like this. Okay. So, this will go like this, and then so the fault here is what we call as an thrust fault. Okay. So, which is common in like compressional tectonic environment. So, this is your thrust fault. Okay. Now, let us see what exactly I am talking about in terms of. So, there is a deformation which is occurring here, like we have compression going on. This block is riding on the top of this, but when in the area, the drainage which is flowing across this is getting affected. So, if you see carefully, then you see a very typical tight meander over here. Okay. And as soon as the eye crosses the fault, okay, the sinuosity reduces and it becomes more or less straight. Okay. So, any channel you take from here, you will find that it is showing a very tight meander, and as soon as it crosses the fault, then it becomes straight. Okay. And even this one also from here, if you take, then you have a very tight meander, and this becomes almost straight and go and meet the major channel. This one is the main trunk stream of in that area, and this goes and meet your Satluj. So, this is one evidence which is an clear indication of the ongoing deformation along the active fault. Okay. So, the another one, this one, what we found was that if you see that what I was talking about, that it shows radial pattern, and when we went in field and found that this is a typical like domal structure, or can we have a warp here, and that is the reason why we are able to see a radial pattern. So, this part in some section we have discussed that. So, if you are having the ongoing deformation in form of an uplift, or you are talking about the subsidence, then the river will tend to have different process which will be operated on along the gradient or along the river profile. Okay. So, in case if you are having an uplift, okay. So, if you are having an uplift here, so in case of the uplift, then you will have this portion will experience erosion. Okay. So, this is we are talking about erosion here, and the upstream of the uplift, okay, the upstream of the uplift and the downstream of the uplift will experience a gradation, that is your deposition. Okay. So, these two areas will have the process which will result into deposition, and this will have erosion. Okay. And also the pattern here, what you see is that you have braided bar braided channels. If suppose you are having, then this portion will have it will have channelized flow, of course, but we will have the landforms which will develop here will be terraces, and further down we will have this similar pattern which we were able to see in the upstream of the uplift. Now, coming to the subsidence, where the profile here, the profile, if you take this as a channel profile here or river profile, so this portion has been uplifted here. Okay. Now, in case of you are having subsidence, and if you draw this profile was like this, so this area is subsiding. Okay. Now, this area is subsiding, that means that you are having a sort of a profile which has gone down here. That means you are having a sort of a steepening of the slope, and that gives you a sort of a gradation here. Okay. So, this is degradation here, this is you are having degradation at the downstream also. Okay. So, this is what you are able to see in both the cases. Okay. So, let us move further and then see what else we have in this one. So, this is a classical example from the Mississippi River in US, okay, which shows a typical indication of when it crosses the uplifted area. Okay. So, this is the area which is in the New Madrid region, and where the Mississippi River, this line, black line is shown as the Mississippi River, and then this area is also experiencing the seismicity, extreme seismicity, and also like is famous for and major earthquake in this region. But usually if you look at the earthquakes which have occurred here are more than 7, also 7 magnitude, but the micro seismicity, if you look at that, then this area is also having like 5 greater than 5 magnitude earthquake and all that, and seismicity keeps continuing in this area. So, we say that this area is an active area. So, the Mississippi River when crosses a 10-meter high topographic warp. Okay. So, you are talking about the topographic warp here like this. So, this is what is you are having is around 10-meter topographic warp. Okay. That is known as, they have called this as they call this as a Lake County uplift. So, this warp is caused due to active deformation in New Madrid seismic zone. So, this is the area of New Madrid seismic zone, and that the uplift or the warping has been caused by that. So, this is the area you have. Okay. So, here the Mississippi River reduces its sinuosity in the upstream. Okay. So, I have a sketch here. So, upstream, suppose we had say that this is the flow direction, then this is an upstream area. So, here what it says that the Mississippi River reduces its sinuosity on the upstream side of the uplift due to decrease in gradient. So, what we are seeing is that suppose you are having, this is the gradient here. Now, there was an uplift here, that means this has been the slope has been reduced here, whereas at the downstream of you will have the increase in the slope. Okay. So, there is an increase in slope, there is a reduction in slope. So, this keep in mind. So, what we are getting here is that when we are having the reduction in slope, the sinuosity is higher. Okay. So, sinuosity reduces and decreases in the upstream of the uplift due to decrease in gradient, this is one, and increases in sinuosity is seen in the downstream side, okay, and that is because of the sinuosity decreases here. So, we are looking at, like for example, so it will have, like if the channel is flowing, so here you will have increase in you say decrease in sinuosity, okay, that is reduce in sinuosity, and then when it crosses this area, then again you will have area will have increase in sinuosity here. So, that we will let us see that part here. So, basically what I was talking here is this is what we are looking at. So, slope or gradient decreases, okay, because you are having an uplift. So, at that point you have decrease in sinuosity, whereas the slope is like you are increasing the gradient here because of the steepening, okay. So, increasing the gradient, the sinuosity also increases. So, reduce gradient, less sinuosity, increase gradient, higher sinuosity, okay. So, this was a very common example which was been observed in this area, and that was related to your tectonic deformation, okay. So, this is what has been shown here. So, in the upstream side you have a reduction in sinuosity because of the reduction in the gradient, and in the downstream of the uplift you have increase in sinuosity. So, this is one very good example of the Mississippi River from New Madrid region, okay. So, this is again that what has been shown here, that you have. So, in the uplift here the sinuosity is because of the reduction, sinuosity decreases, and the lower stream you have the sinuosity increases, and the between there is very less sinus channel, okay. So, usually we use this type of local development of meanders, or local development of tight meanders, or local increase in sinuosity, local decrease in sinuosity, and even for the braided streams and all that locally, which are locally seen, okay, not on the regional scale. Then we have to see that what are the reasons and what are the causes for that, okay. Now, stream gradient index, okay. So, this is another exercise which can be done using your remote sensing data, or if you are having, because if you generate the digital elevation model or digital surface model, and you extract the river profile from that. So, you can use this parameter to understand the tectonics, the influence of the tectonics, and this is what usually most commonly done to understand the overall the intensity of the tectonic influence on the landscape, okay. So, usually this, as I have discussed in many many of times, that in our lecture, that the river profile is taken considering the elevation and the distance, okay. So, and most commonly you will be able to see the river profile something like this, okay. Now, if you want to judge or you want to know that what is your stream gradient index in a particular given point, okay. So, if you want to judge somewhere over here, so you can take or you can take a stretch of the area, and that in that stretch what is happening, you can do that, okay. So, what parameters you need, or what like information you need for this to know the SL index is your the difference in height and difference in elevation you can take, and so considering this area, you can have the difference in elevation at this point, and then length of the difference in length you can take, okay. And the center point you will use to take your, this is because you are studying. So, suppose you are having, this is the drainage. I'll have another sketch for you so that we can explain. Suppose this is the drainage. So, you will, if you want to study this stretch, then this will be your center point, okay. and then from center point you will calculate the length actually. So, that will take it, get you this part. So, with this you can calculate the SL index. Okay. So, stream gradient index is sensitive to rock resistance, to erosion and to uplift. So, this will also talk about the incision in the area and whether this is triggered by uplift or it is related to subsidence. That is basically we are talking about the sensitivity of the area under the influence of your tectonics. Okay. So, it increases with increased uplift rate, that is the SL index will increase. Okay. Higher value of SL in rocks of relative low resistance to erosion may be an indicator of recent vertical uplift. Okay. So, you can also talk about the tectonic events also in that area. So, this is what I was talking about. So, suppose you are having a basin here. So, this is a basin taken and then this is a main trunk stream and you want to do analyze the SL of this region, then what you see is this from the center point you are going to get this L here. Okay. And the difference in this 2 points, at this 2 point you will give you delta L, and the elevation difference you can say you will get from this. Okay. So, if you are having this is the equation, simple equation, delta H by delta L into L. So, you are having the elevation difference 40 minus 20 and then you are having this delta L is 2000 meters, that is difference into your, this is your length. Okay. So, if you take that, that will give you the SL index. Now, like low SL index in the strike slip faulting environment. Okay. So, what we find here that so higher value of SL in rocks relatively low resistance to erosion may be indicator of recent vertical uplift. Now, what there is an area which is of course an active region in US and which is a part of the San Andreas fault system, which are having multiple subordinate faults which are in the area. Now, low SL index, because the low SL index is indicative of that there is not much of erosion. So, there is not much of tectonic activity in this area. Okay. But this region which I am talking about, okay, close to San Fernando is an active region. Okay. Because this area has experienced earthquake and this is one of the most active region, that is your San Andreas fault system. So, why this low SL index in this? Because if you see a low SL values, you will say that there is no much of tectonic activity in the region. The reasons given here are that high indices of SL were found along the southern and eastern. Okay. So, this is your north here. So, this one is if you take north here, then this is your east. Okay. So, it says that the high indices of SL were found along the southern and the eastern margin of San Gabriel mountains. Okay. And this is along this line, both are the area of active faulting. High indices were observed along the this reverse fault, that is this one, Sierra Madre fault region, which corresponds to again a 1971 San Fernando earthquake. Low indices were observed along the San Gabriel reverse fault, that is this one. Okay. However, though the San Andreas is active, low indices were observed. Okay. So, what basically I want to emphasize here is that, so that we usually look for, if there is a tectonic activity, then there will be a high SL index. Okay. But here some regions are showing high, but the active regions also, these are all active faults, but this area, that is your San Gabriel fault system, is showing low indices. Okay. And the San Andreas system fault is showing low indices. Okay. So, why it is so? This is because strike slip fault are usually characterized by a narrow valleys. Okay. with crust rocks which can be easily eroded in the valley, which results into low stream gradient index. So, this is one of the reason we have to look at and keep in our mind before we come down to any conclusion. Now, another parameter or you can use to identify the tectonic activity is basin asymmetric factor. Okay. Now, basin asymmetric factor is that how basin is, if we say that okay, the basin is very much symmetry, then how it looks like. So, we can say that okay, this is my basin here, and then this is at the center I am having the main trunk stream, and then I am having the basin which is the streams are flowing. So, this is my trunk stream which is flowing in the center here. But asymmetry, when we say, then we are having the basin, for example, like this, okay, and the stream is flowing somewhere on the side over here, okay, and then we are having the streams which are, or you have like if the basin either it is like this, or you are having the basin over here and the stream is, the main stream is flowing somewhere over here. Okay. So, this is symmetric basin. So, you are having some symmetry here, and this is asymmetric. Okay. Now, basically what is how the drainage has usually developed is one factor which is very much important is your slope. So, if there is change in the slope of the area, and that could be resulted because of the tectonic tilt, then you can get into the having the asymmetric basins. So, you can find out the AF, that is basin asymmetric factor, okay, and that can tell you that what is the whether the area has gone under the deformation or not. Okay. So, this is how it has been calculated, simple. Okay. AF, that this AR is your this portion of the basin. Okay. So, here it is right, but you can have even the areas over as I have shown. So, this will be this portion we are taking, or what you are looking at this one. Okay. So, this is the area you are taking, this will be your AR, and then whole total will be this one. Okay. So, this whole total basin area is your AT, okay, and this one is your AR. So, if you take that, then that will help you in understanding. So, the tilt factor. So, AF is less than 50 suggests tilting of left hand side and uplift on the right hand side. Okay. So, this is what in the case of what example is been shown here. Okay. So, there is an tectonic tilt on the left hand side. So, this portion has been going up and has tilted. Okay. So, this we can say that this portion has moved up and this has tilted over like this. Okay. And that has resulted into, so the left hand side. So, this is the left hand side of the basin and this is the right hand side of the basin. Okay. So, that you can talk about the tectonic tilt here. Okay. So, if you look at the AF, if the value is coming less than 50, suggests the tilt of the left hand side. So, this is the tilt of the left hand side and uplift on the right hand side of the basin. So, basically you are talking about the right hand side of the basin here, and this is your left hand side of the basin. Okay. So, this is what we are talking about, the uplift here. So, upliftment on the right hand side of the basin, and the tilt which goes is on the left hand side. So, tilt is in this direction. This is what has been given here. So, this is your right hand side and this is your left hand side. Okay. So, and this is the direction of the the till. So, there are more parameters here which you can use to even identify the tectonic influence. There is another one is the valley floor width to valley height ratio. Okay. And this is quite interesting, again similar to the previous two ones. Like if you are having the valley, usually we talk about if you are having the valley is something like this. Okay. So, if you look at this, so this is your width we are talking about, this is the width, okay, valley floor width, and then you are talking about the height, okay, and finally we are working on the ratio between these two. Okay. So, this is, we can say this is the right side and this one is your left side, okay, and this is the base of the elevation of that. Okay. So, this is an equation which is given by Bull and McFadden way back in 1977. So, it is valley floor indices. If you want to talk about, then you have the, you need to talk about the that is the left hand side elevation and the right hand side elevation. Okay. So, with this you can reconstruct that. So, valley incision is another important aspect which can be used to define a relative uplift in the area. Okay. So, cross valley profile can be constructed from topo maps, and as I told that you can also use DMs to extract this information. Valley height width can be measured from distance between the channel, that is your VFW, river channel marked by very narrow valleys crossing the mountains or the mountain fronts shows low value of VF, okay, even sometime low less than 1, and large VF greater than are associated with broader valleys. Okay. So, this is basically what we are trying is that if you are having V-shaped valleys, then you will have VF will be less than 1, okay, and if you are having large wider valleys, like you are having rounded or you can say U-shaped valley, broad valleys, then you will have VF will be greater than 1. Okay. So, what this indicates? Okay. So, we have what we did was that if they were crossing the we took two one of the major river and crossing the different tectonic lines or the fault lines. So, we took that. This is what we have MBT, that is your main boundary thrust, Barsad thrust, Son thrust, okay, Palampur thrust and Jwalamukhi thrust. So, this is in northwest Himalaya, mainly in the Himachal region where the Bias flows across or it crosses many fault lines. So, we took the areas there and use the cross valley profile, and then we looked at that what is the usually the activity which we are able to judge from this in terms of the tectonic activity. Okay. So, we have taken across different fault lines, as I told. So, straight away from here what we have discussed in the previous slide, that if you are having the like V-shaped valleys, then this will be VF will be less than 1. Okay. So, and if you are having broader valleys or U-shaped valleys, then VF will be VF will be greater than 1. Okay. So, this with this information, if you look at, then what we got, the VF here is 11.49. So, this is again and a broader valley, and this is here we are having less than 1. Okay. Mostly here we have slightly greater than, but mostly we are having like in two places we are having less than 1. Okay. So, this indicates that this area is this area is more active, relatively more active, this one, okay, and this one, as compared to you are having this is quite like sort of a dormant area, or maybe not much of activity is taking place here, but these are to some extent this is also active, but not so much as compared to what we call Palampur thrust and main boundary thrust. Okay. So, if it has been suggested that V shaped valley with low Vf values less than your 1. Okay. So, if you are having less than 1, then we are looking at that this is in response to your active uplift. Okay. Okay. Broad U shaped valleys with high Vf values, as we have seen in the case of the Barsar thrust, then the Vf is greater than 1 is indicate that either the, because it is broader valleys. So, we have like the channel has tendency to move in this area and eroded, and it is due to stable base level, nothing is happening much here. So, it will result into the erosion, and if not, if it is subjected to the tectonics uplift, then it will have V shaped valleys. Okay. So, this will have less than 1 values and this will have greater than 1 values, okay, of Vf. Okay. Now, coming to the hypsometric curves, there is another exercise which we can do, and again here what information we are using is related to the drainage basin here. Okay. So, hypsometric curve describes the distribution of elevation across an area on land. So, in this sketch what you see is that we have the elevation here and then horizontal distance, and this is your area of the main overall full drainage. Okay. Now, the curve, again in this we are going to generate curves. Okay. So, curves could be like in different like different patterns, maybe like this, okay, maybe like that, okay, or this is like this. Okay. So, what exactly this type of curves are talking about, where we will be mostly trying to plot the A by A, that is the relative area, and you are having H by H, that is your relative height. Okay. So, the curve is created by plotting the proportion of total basin height, that is your relative height. So, total basin height is this one based on what we will get, that is your H by H, you will see that is your total relative height against the proportion of total basin area, that is your relative area that I was talking about. This is your A by A, this is relative area, and so, and this one is your relative height, and this is what the curve we see that this type of curves we will be getting. Okay. Now, what the shape of the curves has to tell about, okay, that we will learn. Okay. So, total height is the relief within the basin, that is your maximum elevation minus the minimum elevation, then the total surface area, that is A you are looking at, this is the entire basin area A. Okay. And then you are having the area A is the surface area within the basin above a given height. So, this is suppose you have a given height, above that you are having, this is your the basin area, shaded basin area. So, that you are taking about here. So, which the basin portion you want to study, that again will depend. So, the last point we will just see at this curve. So, what it says is that the value of relative area always varies from 1 at the lowest point in the basin. Okay. So, the lowest point will be this one here. So, it will be 1 here, and 2. So, from 1 to 0, and that will be 0 0 will be at the highest point in the basin. So, this is what usually we try to look at, and that you will obtain based on the values you are going to generate of the given area of the relative, that is the given basin based on the relative height and relative this thing. Okay. Now, so this is what we see the curves. Okay. So, this type of curves will be generated where you will have the HI index or the HI values you will be able to see, and again we are plotting the relative height and relative area. So, if you have this type of curves, that is you can say that concave curves, and this you are having convex curves, okay, and in between mixture of that. So, that will indicate over you also you will have you can have the values also, but you can talk about that this is an older stage of the river, whereas if we are looking at the concave, the convex one, then you will say that this is youth stage, and this could indicate, could be indicative of active uplift in the area, okay, or ongoing active tectonics in the region. Okay. Now, this is some part which can be used to understand the local development of meanders and all that. So, in terms of you are having an uplift here, and then you are having subsidence. So, if you have like what type of channel you have before the uplift region, that will result into different type of meanders. So, for example, different type of pattern, river patterns. For example, you are having before just above the this is what is like showing the anticlinal like areas. Okay. So, if you are, so before that, if you are having in the upstream, you are having meandering channel. So, this will get into the braided, and then further down, if you are having this the down faulting, this is up, okay, and this is down here. So, here again from meander it will get into the braided type. Okay. So, that what has been given here. So, if you are having low sinuosity, the sinuosity may increase in the downstream, but if you are having meandering channel, then you will have braided channel here. So, that what has been explained here for this one, he is having you are a meandering, or you are having straight responses, you are having anastomosing ridge. So, that will get into the meandering channel. So, with this I will end here, and we will discuss more like about the remaining part like GPR and the using total station and RTK in coming lectures, and also we will be putting more labs. I hope you will enjoy this course. Thank you so much.